Hello everyone and welcome to the first video for Chapter 6 on verifying the trig identities. The skill objectives for this video are number 1, apply the fundamental identities, number 2, simplify trig expressions using identities, and number 3, verify trig identities. Some of the things that you really need to realize with this, the conceptual objectives. Number 1, understand there's more than one way to verify an identity. And number 2, understand identities must hold for all values of the domain of the functions that are related by the identities. Keep in mind that this first one here is a real important one because since there are a lot of different ways to do each one of these. Don't feel like you are doing something wrong if you're not doing it the same way as I'm doing it or somebody else is. If you do a problem and it's different from what I did or somebody else, make sure to ask. Ask if you did it correctly. You probably did. More than likely, you probably will. But just if you want to make sure, be sure to let me know, and we can go through it and I can take a look at it and see whether or not if there was an error in there. Now to start out with, there are two types of equations that we work with. One is an identity, the other is a conditional equation. Identity is an equation that is true for all values of the variable for which the expression in the equations are defined. Okay. For example, you're familiar with some identities other than trig ones. For example, you have seen something like this. X times x plus 1 equals x squared plus x. That will be true for every single value of x. No matter what value you put in there, every real number, that will always be true. Both sides will be equal to each other. A conditional equation is one where it's true for some values of the variable. It's not true for all of them. For example, a very basic one, 2x plus 4 equals 9. That would be a conditional equation. There are values of x that make it true. There are a whole lot of values of x that will make that thing false. So in the first one up here, this is true for every value of x. No matter which one you put in there, it is going to be true. And this one down here, that is only true for some values, or as in this case, just one value. But there could be 2 or 3 that would work. Now let's get to the fundamental identities. The fundamental identities, these are identities that you are already familiar with. You have seen all of these. Okay, we've talked about them. The first set that we have up here are the reciprocal identities. The idea that cosecant is 1 over sine, and the same that sine can be written as 1 over cosecant. And that's true for secant and cosine, and cotangent and tangent as well. Also over here we have the quotient identities. These are ones that we have talked about. The idea that tangent is sine over cosine and cotangent is cosine over sine. Remember that when we dealt with the unit circle that the x was equal to cosine and y was equal to sine. And remember that tangent was y over x. Thus we get sine over cosine. And cotangent then would be the reciprocal, so we get x over y, so cosine over the sine. Another set that we have are the Pythagorean identities, the idea that cosine squared x plus sine squared x equals 1. And we also have these other 2 versions as well. We'll talk about these in class next time to go through so you can kind of see where those come from. The fourth set that we have are the even-odd identities. Again, we've talked about these a number of times and most recently with the graphing. The idea that with the odd functions, sine, cosecant, tangent, cotangent, when you have a negative angle there, it's like the sine of the opposite of x is going to be the opposite of the sine of x. Tangent of the opposite of x is an opposite of the tangent of x. Those are the odd, and that will be true for sine, cosecant, tangent, cotangent. Then we have the even identities, the idea that the cosine of the opposite of x is equal to cosine of x, or the secant of the opposite of x equals secant of x. Notice on there I will use the opposite instead of the negative there because we know that all these 6 trig functions, sometimes they take positive values, sometimes they take negative values. So when we talk about the opposite, it would either be if the original was negative, then the opposite is going to be positive. So these are our fundamental identities. Now these are ones again that you know now, or you know most of these. And you're going to want to get these things memorized here because these are ones that are going to be showing, they're going to show up a lot as we progress through this section. There is one other set of fundamental identities that we're going to talk about in the next slide. They're called the cofunction identities. Now when we look at the cofunction identities, what we're going to deal with here is we have this triangle, this right triangle. Okay, this angle is alpha, this is beta, we have our right angle. This side has length A, that's B, and that's C. Now some of the things you have to realize up here. Fact, alpha plus beta equals 90 degrees. Or, if we're in radians, alpha plus beta would have to be pi over 2. Now that's going to be important because what I know in this with the if I look at the degrees, I know that beta is equal to 90 degrees minus alpha, or beta is equal to pi over 2 minus alpha as well. Now to see where these things come from, what we're going to do is look at the we'll look at the sine and the cosine of two of the angles. What we'll do is the sine of alpha is equal to opposite over hypotenuse, so I get A over C. And the cosine of beta is also A over C, adjacent over hypotenuse. Now that relationship is going to be true for all the others as well. That in this case, the value of the trig function of one angle is the same as the value of the cofunction of the other angle. So what I can say is I know that the sine of alpha is equal to the cosine of beta. Now that will also be true for other values too. I know that the secant of alpha is equal to the cosecant of beta, and the tangent of alpha will be equal to the cotangent of beta. So now what we're going to do is we're going to take this piece right here and this fact here to come through and give us what are called our cofunction identities. And the first one we get is that the sine of x here is going to be the cosine of pi over 2 minus x, or the cosine of x is equal to the sine of pi over 2 minus x. Another one we have is that the tangent of x is equal to the cotangent of pi over 2 minus x. The cotangent of x is equal to the tangent of pi over 2 minus x. And then the last two, the secant of x is equal to the cosecant of pi over 2 minus x, and the cosecant of x is equal to the secant of pi over 2 minus x. Also remember that each one of these, in each one of these you can replace the pi over 2 with 90 degrees, and that will be another version of this as well. You have two forms of this, both the radian and the degree form, to keep in mind. In addition, we will take a look at a couple examples of problems on how we'll use these cofunction identities, whether we're looking at a verification of an identity or in an application problem. Now let's take a look at a couple examples in terms of simplifying some of these trig functions. In this case, what we have is we're looking at tangent of x times cotangent of x. Now what we're going to do is I'm going to show you a couple different ways I could approach this problem. Okay, option one. What I can do here is use the reciprocal identities. I know that there's a reciprocal identity that relates tangent and cotangent together. Specifically, I have two of them. Either that tangent is 1 over the cotangent or cotangent is 1 over the tangent. I'm going to apply one of these. It doesn't matter which one. I'm going to use the fact that cotangent is 1 over tangent. So option 1 in this case is that I have tangent of x times cotangent x. And I know that's equal to tangent of x times 1 over tangent of x by replacing tangent with cotangent with 1 over tangent, which is an identity. Which that one, when I go through and multiply that, that's going to give me, that will equal tangent of x over tangent of x, which those two just drop off, they cancel out, and I get 1. That's the first option that I have on this one. Option 2 for this one. What I can do is change everything to sines and cosines. Tangent I know is sine x over cosine x, and cotangent is cosine x over sine x. So I can say I have tangent of x, cotangent of x, equals sine x over cosine x times cosine x over sine x. And now I can go through, and by multiplying these out, I'm going to go through, the sines will drop off, the cosines cancel out, and the result there is 1. Two different ways of doing that problem. Both work, both are legal, and you would be fine with either one. And again, I also kind of talked about a third one in that if I had gone through and instead instead of replacing cotangent with over tangent, if I had replaced tangent with 1 over cotangent, it would have been very similar to this one. Now, let's take a look at this second version. The second one, cosine squared x times the quantity tangent squared x plus 1. Now, option 1 here, I can use the fact that tangent is sine over cosine, and I can replace tangent squared with sine squared over cosine squared. So I'll have cosine squared x times sine squared x over cosine squared x plus 1. At this point, I can now distribute the cosine squared. So if I distribute the cosine squared, take cosine squared times the sine squared over cosine squared, the cosines will drop off. I'll end up with sine squared x plus cosine squared x. So these would all be equal. And then by the Pythagorean identity, I know sine squared x plus cosine squared x is equal to 1. So there would be this version here that simplifies to be 1. It is just a coincidence that these both came out to be 1. It doesn't have to be that way. Option 2 on this one, I'm going to use the idea that instead of, like here in this first example, first part option, I went through and used the Pythagorean identity at the end. I'm going to use that in the beginning. I have a Pythagorean identity that says tangent squared x plus 1 is equal to secant squared x. So with that, I know that cosine squared x times tangent squared x plus 1, that's equal to cosine squared x times secant squared x. And again, by the reciprocal identities, I know secant is 1 over cosine, so secant squared would be 1 over cosine squared, so I get cosine squared x times 1 over cosine squared x, and when you multiply that out, I get 1. And so, again, two different ways of approaching this problem. Again, both are correct. Both would get you full credit. It's just however you decide to start the problem and work through it. Now let's take a look at this a third example. This time we're just going to approach it one way. And so what I have with this one here, I want to go through and simplify this expression down as far as I can. And what I'm going to do on this, there's a couple different ways we could go about this one. Option one would be to write this as a fraction, get a common denominator, combine them. Option two, though, I think is going to be a better way. And what we're going to do is we're going to go through and use a Pythagorean identity. I know that sine squared x plus cosine squared x equals 1. And so by solving that for cosine squared, I can find that cosine squared x is going to be 1 minus sine squared x. And so I know this thing right there, by Pythagorean identity, that's going to become 1 minus, and in the numerator, 1 minus sine squared x over 1 plus sine x. And now what I'm going to do here is a little bit of algebra. I'm going to go and factor this, okay? That 1 minus sine squared, that is actually a difference of two squares. And you might recall that we know a squared minus b squared factors as a plus b times a minus b. So it's just a matter of identifying what's in the a spot and the b spot. So in this case, a would be 1, b is sine x, and so this becomes 1 minus, in the numerator up here I'll have 1 plus sine x times 1 minus sine x all over 1 plus sine x. Now at this point here, I do have a common factor that I can deal with. Okay, so in this case, this 1 plus sine x and 1 plus sine x drops off. And so what I now have is 1 minus, in parentheses, 1 minus sine x. Distribute that negative sign, that's going to be 1 minus 1 plus sine x. So I combine all the like terms, and the final answer on this is that this is just equal to sine of x. Now we get to the verifying identities aspect. Now some guidelines, and again, it's important to remember these are guidelines. They are not hard and fast rules. I say this every year to students. If I could tell you a single way that if you went through this process you would get every single one of these right, I would tell you. But I don't have that option because it doesn't exist. In this case, these are guidelines. They are a way to start, but they are by no means the only way to do it. And in some cases, it's going to be better to throw the guidelines out the window, and there's other things that will make your life a little bit easier. So it all will come with practice. So don't get too worked up about these. Do the best you can. They do get easier as you progress through these and you start to recognize the identities and some of the things that are happening. The first thing that you want to do, and this is one that it's always been the case, never seen where it wasn't, is one, you want to start with the more complicated side of the equation. That's the one you want to work with. Again, these are verify the identities. These are actually proofs. And one thing I do have to say about this, and with this as well, all your properties of equality cannot be used. The reason they can't be used is because you are trying to prove equality. You cannot use properties of equality to prove equality. You get into a circular logic, and that is a very bad thing. So what that means is that you must identify and work on one side of the equation only. The side you're going to want to do is the more complicated looking side. You want to find that messy side. Now, sometimes what you want to do is combine all sums and differences of fractions into a single fraction. A lot of times that's a good way to start. Again, it's by no means the only way, and sometimes it's not going to be the best way. You just have to recognize it. In fact, we'll show you an example in class on where actually doing this part would not be the best thing initially. You want to look to apply a fundamental identities. Go ahead, then use some more algebra techniques to kind of try to manipulate that one side so that it starts to look like the other. But remember, as you do this manipulation, sometimes you're going to have to go back to using a fundamental identity. And as you'll apply a fundamental identity again, do some more algebra, and eventually you get to the point where you get to the one side matches the other. Another thing you have, and it's not always going to be the case, but sometimes it is helpful, just to convert all trig functions into sines and cosines. You have identities that do that. You know secant, cosecant, tangent, cotangent, what they are with respect to do with using just sines and cosines. So sometimes that's what you're going to want to do. Let's take a look at a couple examples. In this case, I want to verify, in the first one, I want to verify that cosecant of x minus sine x is equal to cotangent x times cosine x. So what I'm going to do with that is I'm going to go through on this one, and I can choose whichever side I want to work on. I'm going to go with the work on the left side. So I will recopy that, cosecant of x minus sine x. Now in this case, what I'm going to do is I'm actually going to convert everything to sines and cosines, because that actually will be the best way to go on this one, I feel. And what I'm going to do on this is I can say cosecant is 1 over sine, so that's going to be 1 over sine x minus sine x. And I want you to think of that as over 1. And now remember, we want to combine these into a single fraction. So I have to get the common denominator. And so that is going to equal 1 over sine x minus, now in this case my common denominator is sine x, so it's going to be sine squared x over sine x. And so when I combine these into the single fraction, that's going to be equal to 1 minus sine squared x over sine x. Now, at this point, looking at this 1 minus sine squared x, you should be thinking about Pythagorean identity. When you see 1 in trig function squared, a lot of times you're going to be thinking Pythagorean identity. In this case, it would be the correct move. I know that 1 minus sine squared is equal to cosine squared, so that's going to be cosine squared x over sine x, which that can be written as cosine of x over sine x times cosine of x, because one cosine can come down, which that cosine over sine, that's just equal to, cotangent x cosine x. And so in this case, we are now done with this problem. We have shown, we've taken the, right here, we've taken that left-hand side, this part, and we've converted it into this. We've changed into that. And that's the idea behind verifying identity. Notice at no time did I add or subtract something from both sides of that equation or multiply both sides by something. Now let's take a look at this second problem. In this case, what I'm looking at is the cosecant of negative x minus 1, or opposite of x minus 1, equals cotangent squared over cosecant of the opposite of x plus 1. Now the first thing I'm going to do here is deal with that negative angle. And so I know that's going to be negative cosecant of x minus 1 equals cotangent squared x over negative cosecant x plus 1. So now on this particular problem, what I'm going to do is I am going to go and use a Pythagorean identity. I know cotangent squared x is equal to cosecant squared x minus 1. So I'm going to start out, I'll use my right-hand side as the messier side. So I now have cotangent squared x over, instead of negative cosecant x plus 1, I'm going to write it as 1 minus cosecant x. And I know by Pythagorean identity that cotangent squared is equal to cosecant squared x minus 1 all over 1 minus cosecant x. Now at this point, what I need to do is factor out that numerator. Again, it's a difference of two squares. So that's going to be cosecant x minus 1 times cosecant x plus 1 all over 1 minus cosecant x. Now at this point, you're looking, wait a second, these two here and here look very similar. And they do, they're just opposites of each other. And so what happens is that when these two pieces here cancel each other out, which they will do, I'm going to be left with negative 1, because these, again, these are opposites of each other. Positive cosecant, negative 1, positive 1, negative cosecant. And so these will cancel each other out, but I'll be left with a -1 there. And so this is going to equal -1 times the cosecant of x plus 1. And when I distribute the -1, I get negative cosecant x minus 1, which is what we have on the other side. So this will conclude the video for now that we have. A lot of what we do on this one, it is with these problems, it really depends on your ability to work through problems. So I will do, like I said, a couple more examples. I'll talk a little bit about the Pythagorean identities. But overall, most of the time in class is going to be spent working through these problems. So with that, I hope you are having a good night, and I will see you at our next class.